All right, hello everyone. I'm excited to talk to you today about a model that we have been developing to explain inference reasoning of the interactions between objects in simple physical events and some of the new predictions that we have been testing. And I would like to start with a little mystery, which is when 12-month-olds watch an event in which a big yellow duck goes behind a screen, and they're surprised when the screen lowers to reveal a duck that is small, green, and dotted. Many studies using tasks like this have found that by 12 months, infants can use many types of feature information like size and pattern to detect violations in physical reasoning. And yet, if we change the event just slightly, such like a big yellow duck emerges on one side of the screen and then goes back behind, and a small green dotted duck comes out the other side of the screen and goes back behind, infants at 12 months are not surprised when the screen lowers to reveal only a small green dotted duck. So why is it that infants can use feature information to detect violations in physical reasoning, but not individuation violations? We have proposed a new model to reconcile these seeming inconsistencies across different types of reasoning tasks. And today I'll focus on how our model explains infant successes and failures in object individuation. Let me first quickly describe the model with its main assumptions, and then we'll talk about the new predictions. So first, we assume that at least two different systems work together to represent a physical event. The object file system builds temporary representations of objects that we encounter. It represents the spatial, temporal, and identity information about objects. And for each of those, it uses both categorical information and more fine-grained features. So for example, a duck is a categorical descriptor at the basic level for 12-month-olds, and small, green, and dotted will be the features. The physical reasoning system, on the other hand, is a causal reasoning system that reasons about the interactions between objects. And so it only comes into play when we have a causal interaction between objects. Our second assumption in the model is that the two systems need to communicate with each other throughout the course of an event about the objects involved in order to monitor and predict its outcome. And here are some of the main steps in which they interact with each other. At the beginning of the event, the object file system passes on to the physical reasoning system all the categorical information that it has about each object. Then the physical reasoning system categorizes the event and assigns event roles to the objects involved. For example, the duck event you saw will be categorized as an inclusion event with an includer and includees. The physical reasoning system then requests from the object file system specific features that it has learned over time to be causally relevant for that particular event category. And it uses both the categorical and feature information it has available to monitor the event and predict its outcome. Now, our model's third assumption is that when an event comes to an end, the two systems must jointly decide how many objects are present in the event so that they can continue to track and monitor the objects into the next event. So how do the two systems determine how many objects there are? Well, our assumption here is that the object file system uses primarily categorical information to do that. The physical reasoning system uses the same categorical information, but it also uses features that it has identified over time to be causally relevant for that event category. And because the two systems use slightly different information to individuate, they will sometimes agree, but sometimes disagree. Now, in a physical event in which the same big yellow duck appears on either side of the screen, both systems will agree that one object that is non-human, closed, and self-propelled is behind the screen, and so we have no problems. The infants will expect one object to be revealed when the screen lowers. When two different ducks emerge in alternation, however, we have a problem. In 12-month-olds, the object file system thinks one object that is non-human, closed, and self-propelled is behind the screen. The physical reasoning system, however, uses the same categorical descriptor, but also, in addition, it has identified size and pattern to be causally relevant for occlusion events. And so it thinks that two different ducks are behind the screen. In this case, the two systems disagree about the number of objects that are present. And the physical reasoning system at this stage might signal to the object file system that two objects are present, and so you should create a new file for that second object. However, the object file system has just one categorical descriptor, and so it doesn't have a way to split that index or create a new unique index for the second object. And so this disagreement cannot be reconciled between the systems, and we predicted that this would lead to a catastrophic individuation failure, meaning the infants will have no expectations at all about how many objects there should be behind the screen. And that is what we found in a previous study. After seeing two cups that are only featurely distinct emerge on either side of the screen, 12-month-olds were not surprised when the screen lowered to reveal nothing behind it. So infants continue to fail in these kinds of individuation tasks until they're about 13, 14 months of age. Thus far, we have seen one scenario in which the two systems agree and one scenario in which the two systems disagree, as well as their consequences for infants' individuation. Now I'd like to turn to two new predictions of our model that deals with helping the two systems come to an agreement, leading to successful individuation. The first prediction has to do with categorical information. We predicted that infants should be able to individuate objects as long as we can induce the object file system to assign distinct categorical descriptors to the objects involved, as the categorical descriptors will allow the two systems to communicate about the objects involved in an unambiguous way. Now, we're not the only ones to highlight the importance of categorical information. Past studies, including many that are done in Hungary, maybe even by folks in the audience, have used different types of manipulations to induce the object file system to encode, for example, basic level categories or functional categories. However, these prior work all suggest that the categorical information is conceptually rich and meaningful. Our account differs in that we assume any type of contrastive categorical information should work, meaning that even with indices where tags are temporary in nature or provide very little information of objects, should allow the two systems to communicate unambiguously. We tested this prediction in a recent paper. In one experiment, 14-month-olds first saw two featurely distinct cylinders, the ones shown here, and they play different roles across two different support events. In one, a striped cylinder is supported by a block, and in the other, a star cylinder provides support for a different block, so they play different roles. Then infants saw a typical individuation task in which the two cylinders emerge in alternation on either side of the screen. Then the screen is lowered to reveal only the last to appear object. We found that infants were surprised to see the individuation violation in this case, suggesting that the two systems were able to use the distinct event roles, formally a support and formally a supportee, to come to a 2 versus 2 agreement, and they can individuate objects. In a second experiment, even just seeing simple static displays of blocks and cylinders were enough to help 9-month-olds individuate the objects in a very similar individuation task. And so our results in that study confirmed our first prediction that infants can use any type of contrastive categorical information to individuate. The second prediction of our model, the one that I'll be presenting new data on today, is that some disagreements between the two systems can be reconciled, leading to successful individuation. These reconcilable disagreements arise if the last seen object in an event remains visible when the event ends. Now let us return again to the example individuation event with the two featurely distinct ducks. At the end of the event, after the last seen object has returned behind the screen, the object file system will point to the screen and think that only one object is hidden based on categorical information. But the physical reasoning system thinks there are two based on also featurely distinct information. This disagreement leads to a catastrophic individuation failure and no expectations. Thus, infants will not be surprised when the screen lowers to reveal just one duck. If, however, the last to appear duck remains visible next to the screen like this, the two systems will now make two judgments. First, they will agree that one object is visible and is present here, and so there's no problem about that. Second, they still need to determine the number of objects that are present behind the screen. So the object file system thinks nothing is hidden, as the only thing it was tracking based on categorical information is currently visible. But the physical reasoning system thinks there is still one more object hidden based on causally relevant features. And it's going to ask object file system to add one more file. In this case, the object file system can use distinct spatial temporal categorical information behind the screen to posit a new file. And so they come to an agreement and leading to successful individuation. And let me back. And so infants should be surprised when the screen lowers to reveal nothing behind it, leaving just one duck in the event. To test this prediction, we asked in the experiment, when the lasting object remains visible at the end of the event, occlusion event, can 11-month-olds individuate 2 or even 3 objects? And we used a violation expectation looking time task. Each event saw just one test trial in which they saw a live event, and they were randomly assigned to one of 3 between participants' conditions. In the one object condition, infants first saw a hand bring out a block on one side of the screen and then taps it, and then goes back behind the screen, and then the hand brings out another identical object on the other side of the screen, taps it, and then brings it back behind the screen. And this sequence is repeated 3 times. In the 2 objects conditions identical, except that infants saw 2 featurely distinct boxes on either side of the screen. For example, a blue stripe box and a green checker box. The 3 objects condition, as you might guess, infants saw 3 featurely distinct boxes. Now, within each condition, infants were randomly assigned to see one of 2 kinds of endings. In the hidden at the end event, infants saw the last to appear object go behind the screen, and then the screen was lowered to reveal just the last to appear object. In the visible at the end event, however, the last to appear object remains visible next to the screen as the screen is lowered to reveal nothing behind it. So the 2 events end in identical ways with just one object on stage. Now let me unpack quickly our model's predictions and then show you the results. So in the one object condition, both systems will agree in both events that only one object is present, either behind the screen or visible next to the screen. Our predictions are different from the 2 objects condition, where in the hidden at the end event, the 2 systems would disagree about the number of objects, and they cannot reconcile that disagreement, and so infants should have no expectations here. In the visible at the end event, both systems will agree that one object is present, but they will disagree about the number of objects are still hidden. But this 0 versus 1 disagreement can be resolved, and so infants should be able to individuate here and be surprised when they see there's just one object at the end of the event. And our predictions are very similar for the 3 objects event. It's just that there will be 2 objects. The physical reasoning system will think there are 2 objects. Now for the results, you'll see violin plots of infants' looking time at the end of each event. On the y-axis, you will see their raw looking time in seconds, and there will be 3 panels, one for the 1 object, one for 2 objects, and one for 3 objects. And within each panel, you will see the hidden at the end event on the left and the visible at the end event on the right. Now in the 1 object condition, what we found is that indeed there's no difference in infants' looking time, suggesting that they were okay with the end of the events in both of these events. In the 2 and 3 objects events, however, we found that infants who saw the visible at the end event looked significantly longer than the infants in the hidden at the end events. Okay? And so in this experiment, when the lasting object remains visible at the end of the event, 11-month-olds can individuate 2 and even 3 objects. These results confirm our model's second prediction that nothing versus 1 and nothing versus 2 disagreements can be resolved, and the reconciliation lead infants to detect individuation violations. Now in the future, we would like to flesh out more details of the model. For example, we assume that the physical reasoning system can ask the object file system to add 1 or more new files to reconcile a 0 versus 1 or 0 versus 2 disagreement. How might that work? Would the object file system add an exact number of indices or tags, like exactly 2, or would it add something that's not 0? What about the identity of the objects? If the object file system could add an exact number of files, would each file have precisely the features that were associated with that object in the event? Or would it have a mishmash of all the features that appeared? Or would the object file system simply have no idea what features to expect at all? And finally, in addition to fleshing out the model, we have also been working to extend this model to other types of tasks like position binding. Quite a few studies have looked at how infants remember which objects are where behind multiple screens. In this case, though, we are interested in asking how they bind objects to specific positions behind a single occluder, so a single location. In this case, the categorical descriptor is the same for both objects. They're just behind the screen. And so they have to use feature information left and right behind the screen to bind the objects. And so the two systems cannot use distinct tags to communicate with objects. Like with individuation, our model predicts that infants will succeed if the objects can have distinct categorical descriptors that allow the two systems to communicate unambiguously. And this is what we are testing and have found in a study that we're writing up and hoping to share with you soon. So please stay tuned. So thanks so much for your attention, and I would love to hear your thoughts and questions.
Thank you so much. Any questions? Over there. Yes, over
there. Hello. I'm wondering regarding the, I'm not sure at which age, but young children seem to, at some age, get the concept of psychological continuity. So they follow the story that there's this prince, and he kind of gets in the story, gets converted into a stone, and then gets converted back into the prince. And they have the understanding that it is the same entity. So I'm wondering if this two-object model explains that phenomenon. That is question number one. And question two is, why did you particularly choose this model in lieu of other alternatives? Thank you.
Yeah, great question. So let me maybe talk about the second one first. So we worked on this model because we want to have a very comprehensive model can explain physical reasoning, individuation, and potentially position binding as well. There are other models as well, and our model is actually built on many different previously proposed models that all explain some of the data that we have about how infants reason about the interactions of objects, but none of them can explain all the data. And we think that our model today actually can describe all of the data so far, and actually also makes interesting predictions that we can test that are very testable. So hope that answers your second question. And so the first one about transformable objects. There are actually studies done with infants showing that they also understand if you show them that an object, let's say I think a carrot can transform into a rabbit back into a carrot, they have no problem individuating, like understanding that's possible. And so in the event, they would be okay with, I think they would expect just one object. If you show them a carrot goes behind, actually I'm not sure if this is being done, but basically, they do understand that objects can transform. And so in our model, I've not thought about transforming objects in our model, but I would think that if they already have that information about the object to begin with, then they would be able to use that information in the model. And so imagine if they see the object that they know can transform into a rabbit. It goes behind the screen as a carrot, comes out the other screen as a carrot, goes back again, the screen lowers, reveal, let's say, well actually comes out the other end as a rabbit, goes back behind the screen, lowers, and there's only one object, maybe just the rabbit. Because I know that the object can transform, I would expect them to not be surprised because I knew that that's the property of the object, the fact that it can transform. And so we would expect in this model that they would not be surprised. I think one possibility.
Okay, we have one more question over there.
Hi, thank you for the nice study, very interesting and nice presentation. I have two questions. The first question is, if you could clarify what was like the event that was visually presented to the babies in the visually visible in the end events, because I couldn't understand how there could be an object that is visible at the end on the side of the occluder, and then when you lower the occluder, there is only one object appearing from the head occluder in the scene. So I couldn't reconstruct the spatiotemporal sequence. And that's the first question. I can tell you the second one now, or I can wait. What do you prefer?
My memory is terrible, so let me just answer them
Wonderful.
one at a time.
Mine too.
So, great question. Sorry about that. I had to skim through the procedure quite quickly, so sorry if that wasn't clear. So in the visible at the end of the event, what happens is you will come to the last appear object, so the last repetition where the object is out, and then the screen will remain raised, and the object will remain next to it. And then the screen lowers, there's nothing behind the screen. And then the hand brings the object, the block, back to the center, and then rotates it. So at the very end of the event, the hidden at the end and the visible at the end events are identical. The critical difference is that in the hidden at the end event, the object is already behind the screen when you lower the screen. But in this visible at the end event, it's visible, and when you lower the screen, there's nothing behind it. Yeah, that's actually really important, so thank you.
Thank you so much. That's very helpful. So then my next question is, you are describing this task, whether like the focus of the child, of the competence that this task is tapping on is object individuation, which is correct. But that's not the only kind of requirement of this task. The other, if you want, is working memory, in the sense is maintaining information about the object while the object is occluded. And I'm wondering whether is it possible that the benefit of the object visible at the end effect is that you can use, more kind of sensory information as a working memory support that allow you to keep, allow the baby to maintain the representation of at least two objects being present in the scene, while in the not visible in the end condition, they have to do everything in their working memory for the occluded object.
Yeah, great question. I think working memory could definitely play a role in our model. It's not explicit, but it is definitely a part that's going to play a really important role. Now, when it comes to this particular comparison, I think the question is then, what's the number that could be represented? What are the set of features that are just enough that they can represent? I'm specifically thinking about this because we have 3 objects and 2 objects event, right? And why is it that, so in the 3 objects event, when object is visible, you still have to reason about 2 objects behind the screen, and that seems doable. But in the hidden at the end event, when you have 2 objects, it's the same number of objects that's behind the screen, and yet you cannot do it there. And so why is it that why do you see that difference there if it's about working memory of the object that's behind the screen? Because it's the same number of objects and similar features.
I will need to think about that, but it's not clear to me that there is evidence that they are ever remembering more than 2 objects being there. And maybe one way to test these 2 alternatives would be to see whether having like more objects appearing one after the other, you are going to see like a breakdown due to a working memory load of the working memory of your task is always at 2 objects.
Yeah, it could be. I mean, I think working memory could very well be a limitation here, and maybe we have some evidence for that because you do see in our results that they are successful with both the 2 objects and 3 objects events, but they seem to be doing better with the 2 objects. So it could be that we're running into that working memory limitation here. So working memory could definitely play a role.
It would be interesting to see what's happened when you have an extra object appearing.
Yeah, and also then we run into the limitations of the object tracking system, how many you can track, right? We're going up to 3, which might be the upper bound. We might be able to go up to 4, but we don't know. But I do expect that maybe it will break down once we get to the upper bound.
Yeah, that would be evidence that they are like individuating all the objects.
Right.
Thanks.
Okay, that's our time. Thank you
Thanks
so much, Yulin.